Hey everybody, and welcome back to Submarine History. Today we're going to continue our briefings on radio, and we're going to call it Radio 201 for Naval Historians. Why? Well, because we're going to go a little more in depth on a few subjects we covered in Radio 101 for Naval Historians. The goal of these briefings is to give you a little more insight and appreciation into radio and its role in World War II. Now, of course, radio and World War II are enormous subjects. We can't hope to cover the entire subject in a few 20-minute briefs, but we'll give it a try. Read the description to this video if you can. There are other informative links, and if you have questions, please feel free to post them below in the comments. Finally, and as always, feel free to stop the briefing at any time to study a slide. Thank you to the United States Naval Institute for doing the work they do to preserve naval history from around the world. Consider supporting USNI with a membership so they may continue their mission long into the future. I do have a Discord. You should be able to grab a server invite from the link that's embedded in the banner for this channel. Our references for today. Since I did the Radio 101 briefing, I found another newer Army reference on radio, and I think it replaces FM 24-18. This new document, ATP 6-02.53, Techniques for Tactical Radio Operations, United States Army, February 2020. It's a fantastic reference on radio theory and operation, and it's suitable for anybody to read. I've put a link in the description to this video so you can download it for your reference. So these are the 5 selected topics for Radio 201. Not going to talk much about antennas here, as that is a whole other beast. But if there is interest, we can do a Radio 202 and we can talk a little bit more in depth about antennas. Because really, your radio is only good as your antenna. Okay, so let's start off with talking about line of sight communication, which is what we associate with VHF and UHF communication. Now, before we get too far, I want to emphasize that everything we're talking about and the calculations we do are all based on ideal conditions, which you rarely have in real life, and which results in our line of sight communication distance being shorter, sometimes much shorter. Having said that, radio and its application at sea is closer to the ideal than on land, where we deal with topography, vegetation, and man-made obstructions. From Radio 101, we know that the VHF band starts at 30 megahertz, or 10 meters, and it goes to 300 megahertz, or 1 meter, where the UHF band picks up at 300 megahertz and goes to 3 gigahertz, which is 10 millimeters. When you watch a World War II movie and there are troops talking back and forth to each other on the radio, think the movie Wind Talkers. Yeah, it's not a great movie, but I appreciate it for its accurate representation of radio use on the battlefield. But that's VHF. Same thing with airplane-to-airplane chatter. The movie Dunkirk is a great example of this. That's VHF. I'm not sure to what extent UHF was used for communications in World War II. I think it was mostly for radar, but I do know that the German Army experimented with UHF radio mesh networks. Mostly, though, we're talking VHF. On the most basic level, you can think of line-of-sight communication as 2 people standing in a field some distance apart, but they can see each other. I can see you, so I have the potential to have communication with you. This is the opposite of over the horizon, where VHF and UHF won't work. We'll get to that later in the briefing. Let's look at it another way. In this picture, you're on a beach with the tide lapping at your toes. You are at sea level. You're looking out to sea with binoculars, and in the distance, you see something jutting a little bit above the horizon. That something is the tip of a mast of a sailboat. There is an equation that can tell us the distance to the horizon based upon how high up our perspective is. The distance to the horizon is equal to a constant k times the square root of the height of our perspective. It's just trigonometry. You can see in this slide that there are 2 forms of the constant. Well, one is for metric and one is for the English system of measurement. On this slide, we can see a 6-foot tall person standing at the edge of the water. the horizon is at a distance of approximately 3 miles. This is an important number because this also represents, in general, how high a periscope would have been above the water in World War II. So if your boat was running at periscope depth, your field of vision is about 3 miles. Could be more, but extending the periscope higher than you need to risks your own detection. So just to finish out this slide, you're 6 feet tall, you have your distance to the horizon is 3 miles. For the sailboat on the ocean, that top of mast is 40 feet, which for that sailboat puts the horizon at a distance of 7.7 miles. So the theoretical line of sight between the observer on shore and the sailboat is the summation of those two numbers, or 10.7 miles. Let's extend this conversation just a little bit more. This is a card from the Office of Naval Intelligence, FM 30-50 Recognition Manual, dated September 1943. And I have a link in the description to this briefing where you can download a copy of that. From the card, we can see the height from the waterline to the bridge and top of match, which is 41 feet and 83 feet respectively. Knowing these heights, we can figure how far a watchstander could see, and that is 7.8 miles from the bridge and 11.1 miles from the top of the mast. I'm not sure if the Fletchers had a crow's nest up on top of the mast, but you could have radar up there, which is also bound by line of sight limitations. And here's a bonus round, since we have the identification card up. We can estimate the distance to an object if we know the size of it and can visualize its size in terms of milliradian, or mils. If you're watching a movie and there is a scene with the view of a ship through a periscope, those little hash marks you see in the periscope, that's a mil scale. And the same thing through the view through a sniper scope. And in this example here, let's just do this real quick. While standing watch, you note a Fletcher sailing with you off to port, and you estimate it's 16 mils from the waterline to the top of the mast. How far away is that DD from your ship? We do the calculation, and the answer comes out to be 5,187.5 feet, or about 1 mile. Using that line of sight equation, we can actually graph out how far you could see and potentially talk, depending on the height of your antenna. In World War II, we would be dealing with that area defined by the red box on the lower left-hand side. A 500-meter tall antenna, which is about 1,600 feet, gives you a line of sight of about 50 to 60 miles. As an example, in the USA, the highest commercial radio TV antennas are about 2,000 feet. In the U.S. Navy, back in World War II, aircraft carriers and battleships had the tallest masts, which could top out at 150 feet. And 150 feet works out to about 15 miles, or up to 30 miles between ships, each with a 150-foot mast. There's a really good book. It's called Condition Red, Destroyer Action in the South Pacific. Again, I'll put a link in the description to it. But in this book, which was written during World War II, there are parts of that book where the author talks about the TBS system, the talk between ships. And that was a low-power VHF radio net that allowed ships within a task force to communicate in the clear with no code or encryption. So that's really it. In general, with VHF or UHF radios, you're limited to line of sight, which is going to max out at about 60 miles for a 2,000-foot antenna. A man-portable radio is going to have a much shorter range, on the order of 1 to 10 miles, simply because of the height of the antenna. Now, earlier, I told you that VHF and UHF communications can't go over the horizon. You know what? I wasn't being completely honest with you. VHF and UHF communications can go over the horizon, sometimes significantly further. And this is because the radio waves will follow the curvature of the Earth a little bit, just past the horizon. And tropospheric ducting events can carry VHF-UH signals way beyond the traditional line of sight. And as a footnote with this slide, an antenna at 3,000 meters could represent an aircraft flying at about 10,000 feet, where its line of sight is about 120 miles. Radio signals attenuate or fade as they travel through the air because of atmospheric conditions, topography, and man-made obstructions. Having an antenna up high is one way to compensate and increases our communication distance. But we can also increase our communication distance by increasing the power of our radio. The intensity of radio waves over distance obeys the inverse square law, which states that intensity is inversely proportional to the square of the distance from a source. So if we double the distance, we're going to have 4 times less power. And like with the antenna height, we can graph how distance changes with an increase in power. As with the last graph, we're primarily concerned with the red box in that lower left-hand side of the graph. This box represents the range of power typically required on ships in World War II for communication systems. Broadly speaking, submarines would have used low-power transmitters in the 50 to 200 watt range, and surface ships would have used higher power equipment, 500 to 1,000 watts, or maybe a little bit higher. Now, as a comparison, modern commercial radio stations can operate at 50,000 watts or 50 kilowatts or higher. But as you can see, this curve starts to flatten just like with the antenna height, and there comes a point where we can no longer add power. But even if you can't extend your distance significantly with more power, you will improve the strength of your signal, which will make it easier for others to hear. So what do we do when we want to communicate with somebody beyond our line of sight? Let's look at the components of a typical radio wave. From the picture, you can see that a radio wave created by an antenna has 2 components. There's a ground wave and a sky wave. Look carefully at the picture. You can see how they depict the ground wave as being tall at the source, or strong, and it gets smaller as it travels. It gets weak. We can associate this type of wave with line of sight. There is a sky wave component as well, and this wave travels upward through the atmosphere where it hits the ionosphere. One of 2 things happens when a radio wave hits the ionosphere. The wave is either absorbed by it, and that's the case with VHF or UHF, or it's reflected back down to Earth. That's high frequency, HF, and lower bands on the radio spectrum. HF is really useful as it allows us to communicate when we don't have line of sight. Think of 2 people on the opposite sides of a hill, or 2 ships over the horizon from each other. This figure gives us a little bit more detail. It depicts the 4 layers of the ionosphere and how HF and lower radio waves interact with it. The takeaway from this figure is that we have a ground wave component that fades out over a short distance, and then we have a sky wave component that travels a long distance before it returns to Earth. In between the point where the ground wave fades out and the wave makes its closest bounce back to Earth is a space called the skip zone. That ground wave could travel up to 50 miles, and it could be 150 miles for that closest first bounce, leaving us a 50-mile zone where we can't hear that radio transmission at all. Here we can see how that HF radio wave can bounce over land a long distance. I don't actually know how many bounces an HF wave can take before it fades out, but I know it can bounce at least a couple times and carry that signal thousands of miles. On this next slide here, you may want to pause this and just kind of study it, but this is a table that kind of gives us some general information about the ranges achievable with the different bands and the range of power required to get that signal out there. So a question you might have is, how do I contact someone on the other side of a hill or mountain, or just over the horizon at sea? How do I avoid that skip zone? There is a principle called Near Vertical Incident Skywave, NVIS or NVIS. We can use this principle with a special antenna to get our HF radio skywave up vertically with little to no ground wave. And that skywave, because of our antenna orientation, will come straight back down in a rain shower effect that saturates an area and eliminates that skip zone. In this example, we're saturating an area of about 100 kilometers. So we can contact the combat unit on the other side of a ridge, or we can contact that destroyer on picket duty way over the horizon from our task force. Also, because the skywave is coming down nearly vertical, it's difficult to direction find, or DF. This looks like a roll cage or the support for camouflaging on this German half-track, but it's actually an ENVIS antenna. The Germans use this to great effect so units spread out on the ground could maintain contact, even if out of line of sight and regardless of terrain obstructions. Another side note, but HF radio and ENVIS are of particular interest to the United States Army today because it provides an alternative to satellite communications, which could be disrupted in wartime. So here we are with our last topic, signal bandwidth. Signal bandwidth describes how much room a particular signal takes up within our frequency band. What this figure tells us, as we're looking at it, is that CW, continuous wave, or Morse code, uses very little bandwidth, which makes it very efficient and useful at low frequencies. If you're sending Morse code on the 10-meter frequency, your signal extends 75 hertz on either side of that 10-meter frequency itself. Its width is 150 hertz total. SSB voice uses 3000 hertz or 3 kilohertz, with AM using 6 kilohertz, and FM ranging from 10 to 15 kilohertz. In World War II, Morse code and SSB voice were widely used because they used little bandwidth and were suitable for the HF band and lower. This is a screenshot from a software-defined radio, SDR, that I run on a laptop. In this figure, we're on the 2-meter amateur radio band at 146.820 megahertz. That's VHF and narrow FM mode. And as you can see from the screenshot, the width or bandwidth of that signal is 8 kilohertz. So it's just below that previous slide, that 10 to 15 kilohertz. This is another screenshot from the SDR. In this figure, we're in the commercial FM band range, and in this case, we're tuned into FM 91.1. Notice how big the bandwidth is. It's 200 kilohertz. This is high-definition radio, and it takes up a lot of bandwidth. Note also the other peaks on the scope. Those are other radio stations, and notice how the radio station frequencies are spread out so they don't interfere with each other. This is an important concept because in World War II, as it is today, there is a finite space on the radio spectrum and everybody is trying to use it. This is one reason why you want your communications to use as little bandwidth as possible, so it's harder for the enemy to find you and you can have more signals in the air. So we'll wrap up the briefing here. On this chart, we can see the total possible channels we can have within the RF bands that are of interest to us. Let's look at the high frequency line. Within that band, we have, if I did the math right, a total of 180,000 possible Morse code channels or 9,000 single sideband voice channels. Well, we don't actually have that many available channels. We might have half that available and actually less because we need to space our channels out so they don't interfere with each other. But that's still a lot. If you've gotten this far in the briefing, you might ask yourself, why even use VHF? Well, you have a lot more available channels, so you can use more bandwidth, which means higher quality audio. And in the modern era, okay, not World War II, we have data. This is digital communication, not analog. This is better suited to VHF and UHF. So that's it for today, everybody. It's a really complex topic that I've tried to distill down. Hopefully you found the briefing useful. And if you have any questions, please post them below and I'll do my best to answer them. Until next time, peace out.